All right, back for part B now. Before we were doing calorimetry for physical processes like putting a hot piece of metal into cold water, which is just a transfer of heat, not a chemical reaction. So that's just a physical process. But now we're going to look at calorimetry for chemical reactions. Actually, calorimetry for chemical reactions is very similar to what we were just doing. It's very similar to calorimetry for physical processes because it's essentially a case where you're transferring energy from one place to another. It's just that with a chemical reaction, you're transferring energy from the system, which is now the reactant molecules, to the surrounding solution, which is made up mostly of water, or the other way around. You're transferring energy from the surrounding solution to the system, which is the reactant molecules. But the concepts are the same. The calorimeter still acts like a small mini universe, thermally insulated from the rest of the real universe. And so we can ignore everything outside the calorimeter. And effectively, the total energy inside the calorimeter remains the same, within a reasonable length of time. Obviously, eventually the heat's going to leak out, but within the span of most inorganic chemical reactions anyway, the total amount of energy within the calorimeter should remain the same. And so the Q of the reaction plus Q of solution should equal zero. Or in other words, the amount of heat lost by the reaction should be the same as the amount of heat gained by the solution, or the amount of heat gained by the reaction should be equal to the amount of heat lost by the solution. So in other words, the magnitudes of Q for the reaction and Q for the solution should be the same, but their signs should be opposite. All right. So the system, again, is just the molecules of the reactants. Everything else is considered surroundings. So that would include the solution, which of course would be made up mostly of water and a calorimeter, and it would include the calorimeter itself. In many cases, we can fortunately ignore any heat absorbed by the calorimeter unless we need extremely accurate results, or unless the calorimeter is made of some material that absorbs a lot of heat. Fortunately, the simplest and cheapest calorimeters are just coffee cups. A couple of coffee cups, one nested in another, makes a pretty good calorimeter. And within a reasonable length of time anyway, the styrofoam in the coffee cup absorbs practically no heat at all. And so in many cases, you can really ignore the calorimeter and still get pretty good results. And that means the surrounding consists of nothing but the solution, basically the water that the reactants and products are dissolved in. So that makes things quite a bit simpler. In this case here, we have got a precipitation reaction going on where we have exactly 100 milliliters of 0.2 molar sodium chloride and 100 milliliters of 0.2 molar silver nitrate, both at 21.9 degrees Celsius, and they're mixed in a coffee cup calorimeter, and the temperature goes up to 23.5 degrees Celsius. Now, in this case, you notice that the problem doesn't say anything about how much water is in the calorimeter. And that's because when we start out, there is no water in the calorimeter. The water comes from the solutions. The 100 milliliters of 0.2 molar sodium chloride, well, that's sodium chloride dissolved in water. And so the volume of that solution is 100 milliliters. That's not 100 milliliters of water, but almost all of that is water. So it's pretty close to that. And the 100 milliliters of 0.2 molar silver nitrate, again, it's mostly water. And so that's where the water and the calorimeter comes from, the two solutions. And they both start at the same temperature, 21.9. Mix them together, the temperature ends up going as high as 23.5. And the side product, well, not the product of the reaction is solid silver chloride. So remember that precipitation reaction, sodium chloride, which is soluble in water, so that's aqueous, plus silver nitrate, which is also soluble in water, so that's aqueous. When they come together, they'll form this is a double displacement reaction. So you get silver chloride, which is not soluble in water, so that's the solid, and you get sodium nitrate, which is soluble in water. So that would be aqueous also. So this is the reaction that's going on. But for most calorimetry problems, you don't really need to know the reaction. You just need to measure the amount of energy. And you do that by measuring the temperature change. And so we want to know how much heat is released by this reaction. The fact that the temperature is going up tells you that the surroundings are gaining energy, and therefore the system, that is the reactant molecules, must be losing energy. So heat is being released as part of this reaction. Or in other words, in effect, heat is one of the products of the reaction. And in order to do this problem, we have to make some reasonable assumptions. First of all, we assume that no heat is absorbed by the calorimeter. And since they said that these are coffee cups, we're assuming that they're styrofoam and that they probably really aren't absorbing any heat. And we have to assume that the air above the solution inside the calorimeter is also not absorbing any heat, which is pretty reasonable. Air does not absorb heat very easily. Okay, and then we also, in this case, have to assume that the specific heat of the solution is the same as the specific heat of water. And that is a reasonable assumption because these are fairly dilute solutions, meaning that the concentrations are not very big. And for a dilute solution, the specific heat is almost always very close to the specific heat of water. And also, we have to assume that the densities of the solutions are about the same as the density of water. And again, that is a pretty good assumption for most dilute solutions. And 0.2 is definitely a dilute solution. And what we want to do is determine the heat released by the reaction from the heat gained by the water. Okay, so we know what the specific heat of water is, or what the specific heat of the solutions would be. And we know that the Q of the reaction is going to be equal to the negative of the Q of water. And so, but again, it doesn't really matter which side you put the negative sign on, as long as one side is negative and the other side is positive. I just put it on the H2O side this time because it just saves us a step at the end of the process. So Q of reaction equals negative Q of H2O. Q of H2O is MC delta T for H2O. Now here, actually, when I say H2O, I'm technically referring to the aqueous solutions of the sodium chloride and silver nitrate. Okay, so keep that in mind. The mass of the solutions, or the H2O as I'm calling it, would be the total mass of the two solutions. You've got 100 milliliters and 100 milliliters, assuming they have the same density as water. That would be 1 gram per milliliter, so 200 milliliters would be 200 grams. So we're assuming the mass is 200 grams times the specific heat of water, and the specific heat of this solution should be close enough to that of water that we can use 4.184 joules per gram degree Celsius, times the change in temperature of the water or the solution, which is final temperature 23.5 minus initial temperature 21.9. And that gives us negative 1,339 joules, which to three significant figures, because you notice all the numbers in the problem were three significant figures, to three significant figures, that would be negative 1,340 with no decimal point. Notice also that it comes out negative, which is correct, because the system, that is the reactant molecules, are releasing heat. They're losing heat. All right, so that would be a negative Q. All right, so you can do it with endothermic reactions too. The chemical reactions that are involved in instant cold packs are endothermic reactions. You've got some substance like, say, ammonium nitrate that's in a plastic bag that's surrounded by water inside another plastic bag. And when you go to, when you twist it or smash it or whatever you have to do, that basically breaks the inner bag and allows the ammonium nitrate to mix with the water. And you get a very concentrated solution of ammonium nitrate. as it happens. Adding ammonium nitrate to water is an endothermic process. It takes in more heat from the outside than it releases once the solution is formed. And so it will draw in heat from the surroundings, and the surroundings will get colder. The surroundings would include things like the surface of the bag, your hand, if it's touching the bag, basically anything that's touching the bag will get colder. And so in this case, an instant cold pack uses 5 grams of ammonium nitrate, that's NH4NO3, in 75 milliliters of water, which of course is 75 grams of water, at 21 degrees Celsius. What is the final temperature of the cold pack, assuming that 1.47 kilojoules of heat is absorbed? All right, so the first thing we want to do is find delta T for the solution. We know the initial temperature, we don't know the final temperature, so we're going to hold the initial temperature off until later. For now, we're going to find delta T. We know that Q of reaction equals negative Q of H2O. In this case, H2O is, I'm just using that to represent the solution because it's actually water and ammonium nitrate. So Q of reaction is negative MC delta T for the H2O. Delta T, rearranging this equation, is just going to be negative Q of reaction over mass of H2O times specific heat of H2O. So that's negative, this was given as 1.47 kilojoules. You need joules to use in these equations because the 4.184 for the specific heat of water is joules per gram degree Celsius. So this 1.47 kilojoules times 1,000 is 1,470 joules. So it's minus 1,470 joules over 75 grams times 4.184 joules per gram degree Celsius. Notice how the units cancel out. Grams here on the bottom cancels with grams here on the bottom of the bottom. And joules cancels with joules, leaving you with degrees Celsius on the bottom of the fraction, which is the same as being on top. So that's where we get degrees Celsius as the unit from. And the number comes out to negative 4.68. So in other words, that's the change in temperature. The temperature goes down by 4.68 degrees Celsius. And that may not sound like very much, but actually, remember, each degree Fahrenheit is about half a degree Celsius. So 4.68 degrees Celsius, that would be over 10 degrees Fahrenheit for the change in temperature. So let's see, the final temperature would be the initial temperature plus the change in temperature. Initial temperature was 21 degrees. The change in temperature was minus 4.68. So our final temperature is 16.3 degrees Celsius. This was kind of a rearrangement of a problem that's solved in the textbook. So they went through all of the steps to solve it, and I decided to sort of turn it around because, one interesting thing that you would really want to know about a cold pack is how cold does it get? So I thought that it made sense to solve it for final temperature. Okay, so sometimes you do have to account for the heat absorbed by the calorimeter. And that would be like, for instance, in cases where you need really, really accurate numbers, or in cases where the calorimeter absorbs a lot of heat. The examples we've been doing so far have been examples where the calorimeter doesn't absorb a lot of heat. But there are some examples of specific type of calorimetry where the calorimeter does absorb a lot of heat, and there's really no way to get around it. So as a little background to that, first of all, the type of calorimetry that we've been talking about so far is often described as constant pressure calorimetry. And it's called constant pressure because the reactions are done in a reaction vessel that's not airtight. Normally, a calorimeter of the type we've been using so far, even if it's just a coffee cup calorimeter, you will want to have a lid on it, just so you don't let the heat rise out of it at will. But the lid is normally not airtight. And even if it is airtight, it's not held on very firmly. So if, for instance, any gases were generated in a reaction that's being done in a constant pressure type calorimeter, the gases would just push the lid off a little bit and escape. And that's what we mean by constant pressure calorimeter. The pressure inside the calorimeter remains the same. And it will be the same as the pressure outside the calorimeter. Whatever the atmospheric pressure happens to be on the day you're doing the experiment, that's going to be the pressure inside the calorimeter too. If the lid were airtight and if it were held on firmly, then any gases that would be evolved in the reaction would not be able to escape. When gases are evolved, that is when things like solids and liquids and aqueous solutions are transformed into products that are gases, they need to expand a lot because gases take up a lot of space compared to solids and liquids and aqueous solutions. And if you can't, if the gases are not able to expand because they're in a container with an airtight lid that's held on firmly, then the pressure increases instead. And in that case, what you've got is a potential bomb, basically. If the pressure builds up so much that the container can't hold it anymore, it explodes. And hence that brings us to the idea of the bomb calorimeter. Bomb calorimeters are useful. They're also known as constant volume calorimeters. I'm going to try to avoid the B word, a bomb, as often as possible because I don't want a visit from Homeland Security once they scan YouTube, which I'm sure they do. So anyway, in this type of calorimeter, we often use this type of calorimeter for reactions that involve gases. We don't like to use constant pressure calorimeters for reactions that involve gases because if your reaction produces a gas in a constant pressure calorimeter that's not airtight, like I said, the gas will just go off into the air and be lost. And the gas can take heat with it. So we don't want to lose the gas. We want to hold it in. And the way we hold it in is by using one of these constant volume calorimeters. And constant volume calorimeter, or the bomb calorimeter, consists of a stainless steel vessel in which the reactants are placed. And that stainless steel vessel is sealed with a very tight fitting lid so it's airtight. And then it's immersed in water. The stainless steel vessel itself is not insulated. So any heat given off by the reaction will be very quickly absorbed by the metal of the vessel and will be very quickly transferred into the water surrounding it. And so the energy that's given off by the reaction will be equal to the total of the energy that's gained by the stainless steel vessel, plus the energy that's gained by the water around it. So if you account for those two things, you should be able to account for all of the heat given off by the reaction. So it's a very similar idea to what we've been doing, except now there are two parts to the equation instead of one. So let's see. Yes, okay. Calorimeter. Using this type of calorimeter is kind of a pain in the butt, though, because it has to be calibrated before each use to determine its heat capacity. The manufacturer will tell you the heat capacity when it comes from the factory, but that can change over time. It can change depending on, if the stainless steel gets dirty or corroded a little bit, or a little chip taken out of it or something like that. That can change the heat capacity. So that needs to be found every single time. Masses are usually not required for this type of calorimetry unless you want to find out the energy of the reaction in joules per gram or kilojoules per mole or something like that. So this type of calorimetry is used very often for things like combustion reactions, because combustion reactions produce large quantities of gases. If you're combusting something organic, that is a compound that consists mostly of carbon and hydrogen, then the carbon will be given off as carbon dioxide gas, and the hydrogen will be given off as water vapor, which is also a gas. And so that's a lot of gas being generated from combustion reactions. An example of a combustion reaction would be, say, 0.963 grams of benzene, which is has the formula C6H6, is burnt in a bomb calorimeter, and the temperature of the calorimeter increases by 8.39 degrees Celsius. This is delta T. We don't need to know what initial and final temperatures are if we know delta T. The bomb, that is the actual metal cylinder that holds the reactants, has a heat capacity of 784 joules per degree Celsius, and it's submerged in 925 milliliters, or 925 grams, of water. And so how much heat is produced by the combustion of benzene? And in practice, Q of reaction is equal to negative Q of the water and the bomb. So in other words, the heat given off by the reaction will be equal to the heat absorbed by the water and the heat absorbed by the stainless steel canister. Okay, the heat absorbed by the water is just MC delta T for water. So Q of reaction is negative mass of H2O times C of H2O times delta T H2O. For the bomb, or the stainless steel canister, the Q, or the heat absorbed, will be the heat capacity times the change in temperature. Notice, and a way to remember this is just to look at the units. For Q is energy, and so we want Q to be in joules. And the heat capacity for the calorimeter is given in 784 joules per degree Celsius. So all you have to do is multiply this by a temperature, or in this case, change in temperature, and you've got joules. And so that's what you do. You take the C of the bomb, that's heat capacity of the bomb, times change in temperature of the bomb. Normally, the change in temperature will be the same for the water and the bomb. So the Q of reaction is going to be negative 925 grams of water times 4.184 joules per gram degrees Celsius for water, times 8.39 degrees Celsius as the temperature change, plus the heat capacity of the bomb, which is 784 joules per degree Celsius, times the temperature change, which is 8.39 degrees Celsius. And so some of the heat released by the reaction goes into the water, and some of the heat goes into the bomb. And when you add the results of those two numbers up, you get negative 39,049 joules, or to put it in reasonable significant figures, I guess that would be 39,000 joules with no decimal point, or negative 39.0 kilojoules. And that would be three significant figures. All right. Now, enthalpy, and I see we're getting close to the time limit for this segment of the video. So I'll give a brief introduction on the idea of entropy. This is section 5.3 in the text. It's on page 255 or 265, depending on whether you're using the hard copy or the PDF. This is finally the last section of the chapter. Well, not finally, this is actually a pretty short chapter. So it's already the last section of the chapter. Enthalpy is based on the idea of the total internal energy of molecules. And the energy in molecules can be stored as potential energy. That's the energy that the molecules have stored up in their bonds. And that's the kind of energy you have to put some energy in during a chemical reaction to break those bonds, but then you get some energy out once new bonds are formed in the products. Plus, molecules, of course, can have kinetic energy. Kinetic energy is the energy of motion, and molecules can have kinetic energy in the form of vibration. So all molecules can have that, whether it's a liquid or a solid or a gas. They all can vibrate. They can have rotation too. Solids don't have so much rotation, but molecules in liquids and gases can have rotation. And also there's translational kinetic energy. That's the energy involved in molecules going from one place to another, around and past one another. Gases have a lot of translational energy, but molecules and liquids can have some translational energy also, but not so much solids. And basically, you can increase or decrease the energy content of the molecules during a process, whether it's a chemical process or a physical process. Potential energy is mostly changed during chemical processes because that involves breaking or forming bonds, and that's what chemical reactions are all about. So you don't really have physical processes that would affect the potential energy. But the kinetic energy can be changed by chemical or physical processes. And the main way that kinetic energy would be influenced would be through thermal energy. Thermal energy can also affect potential energy, but it mostly affects kinetic energy. More thermal energy means faster vibrations, or it means the rotations will be faster, or it means translational energy will be faster, greater translational energy. So in other words, more kinetic energy. Higher temperature means more kinetic energy. Less thermal energy or lower temperatures means slower movement, which means less kinetic energy. The total of all of the possible energies in a substance is known as the internal energy, the symbol being U, a capital U, or sometimes capital E. And changes in internal energy during physical and chemical processes can occur. And we'll see actually in the next segment of the video exactly how that can happen, but I see we're pretty much out of time for this segment. So I'll start there in part C.